Welcome to today's video on total internal reflection. Now, before we get into the total internal reflection theory, maybe it's worth watching a couple other videos that I've already made. The first is on Snell's law, well worth a look, and the second is looking at refractive indices. So please check those out before you watch this video. Some basic revision. We have here a diagram of one medium or material, which is represented by refractive index 1, and a second medium or material that's represented by refractive index number 2. And this diagram allows us to examine what happens when an incident ray comes along from one material and enters into a second material. So for a start, I want to look at three general cases. So the first scenario. In the case where N1 is equal to N2, that represents a ray of light travelling from one medium into the same medium. For example, air into air. In effect, there is no boundary when N1 equals N2. It's just the one constant medium. Here's what the refracted ray would look like. So in this example, if incident light were to travel from the first medium into the second medium, and both mediums are identical, we'd find there's absolutely no bending, or what we call refracting, of the ray. It would travel straight through. So if N1 was equal to N2, the angle of refraction will be equal to the angle of incidence. And of course, both those angles are measured from the normal. So we could say that. Okay, so in this scenario, there is no refraction or bending. The ray simply goes straight through the material. Scenario number 2. If N2 is greater than N1, we're going from one material into a more optically dense material. This might be air into glass, for example. So let's look at what happens in terms of our diagram. If N2 is greater than N1, we find the angle of refraction is less than the angle of incidence. And also, we see that it bends or refracts towards the normal. Okay, if N2 is greater than N1, angle of refraction will be less than the angle of incidence, and the light beam will refract, that is bend, towards the normal. And finally, scenario number 3, if N1 is greater than N2, what happens to the angle of refraction then? So this might be light travelling from water into air, for example. So in this third case, if N1 is greater than N2, we find there is bending of the refracting ray, and that angle of refraction is now greater than the angle of incidence, and it has moved, or rather refracted, away from the normal. So there's our three scenarios. If N1 is equal to N2, the beam travels straight through. If N2 is greater than N1, we find it bends towards the normal. And if N1 is greater than N2, we find there's refraction away from the normal. There's our three scenarios. Let's now look at the critical angle. A quick recap. If N1 is greater than N2, we find that the angle of refraction is greater than the angle of incidence. And we can say that the beam refracts away from the normal, or bends away from the normal. Now, if you continue rotating this angle of incidence, you can do this until you reach a particular angle called the critical angle, theta with a little subscript c for critical. At this particular angle, what we find is the refracted ray refracts all the way around perfectly to the boundary. So here we have it. An incident ray at the critical angle generates a refracted ray of 90 degrees. At the critical angle, which is a particular angle of incidence, we find the refracted ray bends a total of 90 degrees. Let's now bring in Snell's law. Okay, here's Snell's law. Let's look at this particular scenario. We know the angle of refraction is 90 degrees. So let's substitute that in for a start. And most students would be aware that sine of 90 equals 1. So when I multiply n2 by the sine of 90, which is 1, I'm left with n2. Let's now divide n1 across the right-hand side of the equation. And of course, to get the angle of incidence by itself, we need to do the reverse function of sine, which is inverse sine. Now, this is a special case where we have a complete 90-degree refraction, and so we don't just call this the angle of incidence, this is called the critical angle. So we use the symbol theta c for the critical angle. This is the equation that allows us to work out the critical angle for any two medium, provided that n1 is greater than n2. Let's now look at a couple of examples. Example number 1. Calculate the critical angle for light travelling from water with a refractive index of 1,333 into air. So refractive index number 1, the material was water, and its refractive index was 1,333. And the second material was air, and it has a refractive index of 1. So n1 is greater than n2, which means it can refract away from the normal and create this critical angle. So let's have a go at this question. So there's our variables, the critical angle and the two refractive indices, n2 and n1, where n1 is to do with the incident ray of light and n2 is to do with the refracted ray of light. The equation is up here. So we substitute our values in. When we complete this calculation, we find the critical angle of light coming from water into air to be 48.6 degrees. Example number 2. Calculate the critical angle for light travelling from glass into air, where glass has a refractive index of 1.5. Okay, let's now set out our variables. And of course we're going to use the critical angle theorem. Let's now substitute and solve. So we've found the critical angle of light travelling from glass into air is 41.8 degrees. So at the critical angle, your incident ray of light refracts a total of 90 degrees from the normal and grazes the boundary or the interface between the two medium. If you increase the angle of incidence to a value greater than the critical angle, we find that refraction no longer occurs, but rather reflection occurs. In this case, the angle of incidence is equal to the angle of reflection rather than refraction. This process where the incident light never enters the second medium is called total internal reflection. Once again, this process can only ever occur if n1 has a refractive index that's greater than n2. If we were to look at optical fibres, we find there's a central cable of glass and some kind of cladding that exists that surrounds that fibre of glass. This diagram, of course, is to scale. So here's the cladding, looking at it from a front-on view, and your optical fibre is in the middle. It's essential in a situation when light comes in and strikes the boundary between the cladding and the optical fibre that it in fact does totally internal reflect. So it hits the bottom between the interface of the fibre and the cladding, and once again it totally internally reflects. And that allows light to travel around the globe effectively in a fraction of a second through this process of total internal reflection.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.